Okay, so welcome to lesson 15. In this lesson, we're going to learn two theorems. We're going to learn Rolle's theorem and the mean value theorem. We're going to gain some geometric understanding of each theorem. We're going to practice identifying the hypotheses for each theorem and verifying the conclusions. And then we'll also use the mean value theorem in some applications. First, we'll start with Rolle's theorem, which really is just a special case of mean value theorem. So one fun way to kind of remember Rolle's theorem is to get from one point to another smoothly and continuously, in other words, differentiably, you have to roll. Here is the theorem. If f is a function that satisfies the following hypotheses, these three, the function is continuous on the closed interval, a to b, meaning a is less than or equal to x, which is less than or equal to b, and it is differentiable on the open interval, ab, meaning a is less than x, which is less than b, and the function sends a and b to the same y values, then there has to be at least one number in the domain, x equals c, strictly between those endpoints a and b, such that the derivative there is 0. And let's just illustrate 4 cases to see why this would be the case. All right, so say the function sends a to f of a and b to f of b, and those are the same y values. So one option is that we just have a constant function, y is always f of a, y is always f of b. If that's the case, the derivative is always 0, right? The slope of a horizontal line is always 0. So there are, in fact, an infinite number of c's in between a and b where the derivative is 0. Maybe the function sends a and b to the same y values, and maybe this function is increasing initially. Well, since it's nice and smooth and continuous, it's got to eventually start decreasing. The smoothness matters here because if we had a sharp corner, the derivative doesn't exist here. But if you're going to be nice and smooth and continuous, if we're increasing, we're going to have to eventually decrease to get down to that same y value, since f of a is equal to f of b. So there's at least one place in the domain, strictly between a and b, where the derivative is 0. Again, say the function sends a and b to the same y value, and maybe the function starts off by decreasing. Well, eventually it's going to have to start to increase because my function is continuous and I have to get up to this point. That's what we mean when we have to get from one point to another, you gotta roll. Here I am rolling. There's a place in the domain strictly between a and b where the derivative is 0. Our last case is maybe the function starts off increasing, maybe it decreases, eventually it's going to have to increase again. You could do this more than once. In this case, there are more than one places where the derivative is 0. And they happen, again, at x values strictly between a and b. Right? And those are all the cases. To go from one point to another, either you go straight there and the derivative is 0 everywhere between a and b, Or maybe you increase, since you got to get down to this point, you're going to eventually have to decrease. So there's at least the one place in the domain where the derivative is 0. If you start off by decreasing, you're going to have to increase eventually. Again, at least that one place where the derivative is 0. And maybe you increase or decrease more than once. In my picture here, we've got it increasing, decreasing, and then increasing again. There's going to be at least one place, in my picture here, 2 places where the derivative is 0. And that's Rolle's theorem.